In this example 5, we are going to determine the concentration of a substance J as a function of conversion for a gas-phase reaction. Here we have a mixture of 28% of SO2 and 72% of air, both of them charged to a flow reactor in which SO2 is oxidized to SO3 by the reaction SO2 plus half of oxygen will give us SO3. The initial stoichiometry table is given as table E3/5.1. Initially, 72% of the total number of moles is air containing 21% of oxygen and 79% of nitrogen, along with the 28% of SO2. So, Fa0, the molar flow rate of A, in this case SO2, going into the reactor is going to be 0.28, which is the percentage of SO2, times Ft0, the total molar flow rate. And Fv0, which is oxygen, is going to be 0.72, which is the percent of air, but of that 0.72, 0.21 is oxygen, so it's going to be 0.72 times 0.21 times Ft0, the total molar flow rate initially. So theta B is going to be Fb0 divided by Fa0 is going to be 0.72 times 0.21 divided by 0.28 is equal to 0.54, and Fi for the inert, in this case nitrogen, is going to be Fi0 divided by Fa0 is going to be 0.72, the percentage of air, times 0.79, the percentage of nitrogen in the air, divided by 0.28 is equal to 2.03. From the definition of conversion, we substitute not only for the molar flow rate of SO2, in this case A, in terms of conversion, but also for the volumetric flow rate as a function of conversion. And that's something that we are going to see here. So here we have the stoichiometric table for SO2 plus half of oxygen going to SO3. We have the species in the first column, SO2, oxygen, SO3, and nitrogen. The symbols A, B, C, and I for each of them. Initially, we have Fa0 of A. The change is going to be minus Fa0 because it's going to be consumed by the reaction. And the remaining of A is going to be Fa0 times 1 minus X. For Fb, initially we are going to have theta B Fa0 times Fa0, and then the change is going to be minus Fa0 times X divided by 2, because according to the reaction only we need half a molecule of oxygen for a molecule of SO2. So the remaining Fb is going to be Fa0 times theta B minus 1/2 of X. And so we have similar expressions for Fc, Fi, and F total. So the concentration of A is going to be the molar flow rate of A, Fa, divided by the volumetric flow rate B. And this is equal to Fa0 times 1 minus X, which is Fa, divided by the volumetric flow rate B. If we recall for the equation of the volumetric flow rate in function of the volumetric flow rate at times equals 0, we will remember that is B equals B0 times 1 plus epsilon x times P0 divided by P times T0 divided by T0. If we take constant P, the pressure and the temperature, so we will have that B is equal to B0 times 1 plus epsilon x. And from here, Ca, which is equal to Fa0 times 1 minus x divided by B0 times 1 plus epsilon x, it will be equal to Ca0 times 1 minus x divided by 1 plus epsilon x. So the concentration of A initially is equal to the mole fraction of A initially multiplied by the total concentration. And the total concentration can be calculated from an equation of state as the ideal gas law. And we recall that Ya0 is equal to 0.28, that the mole fraction of SO2. T0 is equal to 500 K, and P0 is equal to 1485 kilopascals. From here, we use the equation that CA0 is equal to YA0 times P0 divided by RT0, and when we substitute the values, we will have that CA0 is equal to 0.1 moles per liter, or moles per cubic decimeter. And if we do the same for the total concentration, but with the pressure, with the expression that the total concentration is equal to P0 divided by RT0, so we will come that the total concentration is 0.357 moles per liter. And now if we evaluate epsilon, which epsilon is equal Ya0 times delta, epsilon is going to be Ya0, because this is equal to 0.28 times delta is 1 minus 1 minus 1 half, because remember that we have SO2 plus half of oxygen that gives us SO3, so it's 1 of SO3 minus 1 of SO2 minus 1 half of oxygen. That times 0.28 will give us minus 0.14. So we substitute these values for the concentration of A and the concentration of B, and then we come to some expressions in which the concentrations are only function of the conversion in the reaction. And that's something that we need, because remember that the volume of the reactors are Fa0 divided by minus Ra against X. And then we need to have the rate in function of concentration and this one in function of conversion. So that's what we are having here. So the concentration of C and the concentration of E of I, the inert, are also in expressions only in function of conversion. And in this table we have for all the species SO2, oxygen, SO3, and nitrogen, we have the concentration of each of them, Ca, Cb, Cc, Ci, for different values of X, according to the equations, the expressions that we just got on top. So we are now in a position to express the rate Ra as a function of X. For example, in the rate law for this reaction, if the rate law for this reaction were first order in SO2 and also in oxygen with K equal to 200 liters per mole second, then the rate law will be minus Ra equal K, which is the rate constant, the concentration of A to the first power because it's first order, and the concentration of B to the first power because it's first order in B2. So that will be equal to K, the concentration of Ca0 square times 1 minus x times theta b minus 0.5x, all that divided by 1 plus epsilon x squared. So with these expressions for the rates in function only of conversion, we obtain this table. So here we have 1 divided by minus Ra is plot against conversion for nitrogen, SO2, SO3, and oxygen.